Okay, thank you very much. So let me just first make a couple of comments on what we did yesterday, and then I will start with the last part of the course. Okay. So one comment we did, I would like to make is that remember that yesterday we saw, say, for these one-cut matrix models, that there were two types of axioms, right? One was this 2 pi it, and this was this at, which correspond to this, had this very beautiful geometric interpretation in terms of cycles in the spectral curve. So you have, something like this, and something like this. And the important thing here is that you see t is a parameter of the theory. T is the top parameter. Okay, so in principle, you can even think about it as a complex parameter. And then, if you see, these quantities were giving you the location of the singularities in the Borel plane. So you can see that here we have a slightly different situation. So this is maybe 2 pi it. This is, maybe let's put it here, at. And you see that as t varies, the location of these singularities varies. Okay, so. So this situation in which you don't have, if, for example, we have a purely numerical series, you wouldn't see this. The singularities will be put at fixed values, right? For example, in pan level 1, in 2D gravity, the singularity was at 8, the square root of 3 divided by 5. So this is a number that doesn't move. But here we have a top parameter, and this will move. And this situation in which everything moves, the location of the singularities, the transeries associated to the singularities will also move. This is called sometimes parametric resurgence. And one thing that people discovered already in the early days of resurgence, which was rediscovered in the string theory and supersymmetric gauge theory literature later, is that is the following. You can ask the question is how, now, for example, as you vary t, the singularities are going to move. Huh? So is this variation with the parameter t smooth, or can there be discontinuities? And the answer is that the variation is going to be smooth, but at some special loci in the moduli space of the theory. So if you think about the moduli space of the theory in which, parameterized maybe by t, there are going to be loci where there will be discontinuous changes in the structure of the singularities, okay? Actually, for example, you could have new singularities appearing, singularities disappearing, and so on. And this is called wall crossing. So wall crossing was very much studied in gauge theories, especially supersymmetric gauge theories, but actually it was discovered in resurgence. It was discovered in the mid-90s by French mathematicians working in resurgence. So they realized that there will be this wall crossing behavior, that some singularities will disappear and appear. And one situation in which this happens, for example, is in quantum mechanics. If you look at WKB periods, which are formal power series, and you look at this, there you have an example of parametric resurgence because the location of the singularities depends on the parameters of the potential, and you have already this phenomenon of wall crossing. Okay. I will probably come back to this at the end of the talk today, but let's now try to kind of summarize what we did. So we see that, for example, in these models of 2D gravity, including very recent models like JT gravity, Virasoro minimal strings, you can actually use the formalism that I developed yesterday to actually calculate non-perturbative effects through resurgence very easily. But of course, the kind of matrix models that we were using yesterday were very limited. These were like Hermitian matrix models with polynomial potentials and so on. Now, if you want to keep understanding the role of resurgence in string theory, it's a very good idea to use large N duals, but in string theory, sometimes the large N duals, even when they are simple and they are represented by matrix models, are not always simple matrix models. For example, in ABJM duality, so in the duality between ABJM theory and string theory, we know that for many observables, we can reduce this to a matrix model, but this is not a simple matrix model. I'm not going to write it here because this would take me a long time, but it's written in the lecture notes. It's not really a polynomial matrix model of the type that Rajesh and I have been discussing. So this is really a very complicated matrix model, And understanding the non-perturbative sectors in this matrix model is not just simply doing this eigenvalue tunneling that I was doing. So even if you restrict yourselves to matrix models appearing in dualities with string theory, the techniques that I developed yesterday are not really enough, okay? Now, another thing that you can say is, you can ask is, what is the next level of complexity to understand resurgence in string theory? You see, resurgence is based on the idea that you can extract information from the perturbative series. And if you now ask yourself in how many string theories we have a good understanding of the genus expansion, well, the answer is that, well, not in many cases. I mean, there are not that many string theories in which we have, say, 3-loop or 4-loop results. The only cases in which you have a systematic understanding of the loop expansion is actually when you have a duality with another system, say a gauge theory, a matrix model, and so on which you can do calculations. Of course, there was the class of 2D gravity models. And now the question is, what are the models in string theory where we have some understanding of genus expansion that we could use to understand resurgence and non-perturbative effects in string theory? And the answer, the kind of obvious answer to this question, what are these models, are these topological string models, okay? So topological strings, in a sense, are the next level of complexity in string theory after minimal strings, okay? And Rajesh already talked a lot about these topological strings, and the reason why people have developed resurgence topological string recently was there was a continuous progress in the last 10 or 20 years in calculating the genus expansion in topological string theory, okay? And this allowed people to test the ideas of resurgence there, okay? So let me tell you what we're going to do. So these are topological string theory on a Calabi-Yau manifold M, and thanks to the lectures by Lara, we know now a lot about Calabi-Yaus. So remember that Calabi-Yaus have two types of, let me write it here. So you have a Calabi-Yau manifold here. There are going to be two types of moduli. There are Keller moduli. Also this Lara explained in her lectures. So there are going to be Keller moduli, and there are going to be complex structure moduli. And topological string, I mean, of course, physical string theory depends on both, but topological string theory is a topological version in which you essentially can choose which moduli you keep. If you want to keep the Keller moduli, you have this A model, and if you want to keep the complex structure moduli, you are working in the B model, okay? And both models are exchanged by mirror symmetry. I mean, giving a full explanation of how topological string theory goes would take me a full series of lectures. Rajesh mentioned these things without also giving you too much details. So I'm going to give you some sort of like a remedial summary of how this goes, because what we want to do is to actually see how resurgence works in these models. The important thing is that the quantities that I'm going to consider depends on this moduli, which I'm going to write as Ti, where I is equal to 1 to S, right? So in the A model, keeping the notation that Lara used, S is going to be H11, and here S is going to be H21, okay? If you have a compact Calabi-Yau, okay? So here, Ti, I'm going to represent the moduli in the A model or in the B model, and the quantities that I'm going to consider here are the free energies at genus G, which are non-trivial functions of the moduli, okay? So these are the quantities that people want to compute. Now, the history of how this was calculated by string theories is a very interesting thing. So for the genus 0, the first calculation of this quantity was Candelas de la Osa and company, who actually, thanks to mirror symmetry, they could calculate this. Then for G equal 1, there were these very beautiful papers by Versace, Cecotti, Oguri, and Baffa, who also introduced a technique called holomorphic anomaly to, in principle, calculate these quantities, in principle, for genus bigger than 2, bigger or equal than 2, but this became very complicated. Versace, Cecotti, Oguri, and Baffa were able to give results for genus 1 and genus 2, say, for the quintic Calabi-Yau that Lara was mentioning in her last course. But this was hard to do. And then there was a very interesting simplification of the story, which was what is called local mirror symmetry. Local mirror symmetry is a trick in which you actually consider Calabi-Yau's which are non-compact. Okay, they are toric or non-compact. So these ones being non-compact can have global symmetries. So these are toric Calabi-Yau manifolds. And so this is a family of models which is different from the ones that Lara was discussing. Essentially here you can allow yourself to have non-compact directions. So the simplest of these toric Calabi-Yau manifolds is you take a P1, so you take a 2-sphere, and you consider the anti-canonical bundle, the canonical bundle that this P1 would have in a Calabi-Yau manifold if it was rigid, okay? So you would have here the couple of line bundles, okay? So the total space of this bundle is formally a Calabi-Yau, but you see that you have 2 compact directions and 4 non-compact directions, okay? And the other example that I like a lot is so this is called the resolved conifold, and this is an example that appears very often. It's in a sense the simplest Calabi-Yau that you can consider. And another example that I like a lot is local P2. And essentially you can take now any 4-dimensional surface, any 2-dimensional algebraic surface, and consider it with canonical bundle, and you get this local surface that people sometimes get. And the nice thing, the thing that it's very important about these local Calabi-Yaus is, first of all, mirror symmetry makes sense. You can still define this would be you want the A model geometries, and then mirror symmetry encodes the mirror in this case. The mirror is essentially an algebraic curve. So this is actually quite surprising. The mirror can be written as an algebraic curve in exponentiated variables. So you see, in the same way that here the actual geometry is not really 6-dimensional because the non-trivial geometry is in a subspace, in a P1 or in a P2. In the mirrors, the whole mirror Calabi-Yau, which would be in principle 6-dimensional, actually collapses to a curve. And this is very interesting because this is going to make contact with the spectral curves in matrix models and so on. So that's why local mirror symmetry has been very powerful in relating Calabi-Yau physics, Calabi-Yau topological strings, to other parts of mathematical physics, like matrix models, like supersymmetric gauge theories, and so on. You can, for example, we know, for example, that n=2 supersymmetric theories are described by curves called Seiberg-Witten curves, and you can actually engineer these n=2 theories and its curves by using local mirror symmetry and so on. Here in this talk, what I'm going to actually use is the fact that for these geometries, these things are particularly simple to compute. And then, people essentially developed these techniques that were hard to develop in compact Calabi-Yaus. They developed them for local Calabi-Yaus, and there was really an amazing progress. So, for example, for the resolved conifold, you get exact results for all G. So you get an exact formula for Fg, a closed formula that I'm going to write in a moment. Then for local P2, you can essentially set up a computer program that calculates the Fg's as far as you want, as far as the computer can, let's put it, okay? And I think here, right now, people can get 200 genera easily. My former collaborator, Jay Gu, has a devoted computer in his office just calculating higher genus amplitudes of local P2, and he told me last time that he got to genus 400, okay? Now, there was also, even in the case of toric Calabi-Yaus, there was a very significant developments led in particular by my colleague and friend Albrecht Klemm. And Albrecht has been one of his obsessions to push this calculation at higher genus. And now even the quintic, you can get to genus 60, okay? So remember that for Bender and Wu to be able to understand the quartic oscillator, they just needed 70 terms, okay? So we can understand the quintic Calabi-Yau by using the 60 genera that Albrecht Klemm and his friends have obtained. So the point here is that progress in calculating this perturbative series has made possible to understand the resurgent structure of this series a little bit better, okay? So, after giving you this sort of motivation, let me actually let's try to understand, what is the simplest example that you can get here, and the simplest example is actually this resolved conical, okay? Because here there is an exact result for Fg for all genera, and actually let me write it here. So the resolved conical, I'm going to use the A model most of the time because the A model is sort of very intuitive. In the A model, you actually consider maps. Remember that Rajesh was also discussing this because when he was talking about the A model, he was considering maps from a Riemann surface to another Riemann surface. His target was another Riemann surface. He was considering these Hurwitz covariance. But in general, in this A model of Calabi-Yau, of topological strings Calabi-Yau manifolds, the model is going to count, in appropriate sense, maps from the Riemann surface sigma G to the Calabi-Yau manifold M. So this Riemann surface will land in a two cycle of the Calabi-Yau, and you can think about the TIs here as the complexified areas of these maps, which are what are called sometimes in string theory Wall-Street instantanes, okay? So the A model counts Wall-Street instantanes. Okay, so let me write the formula for Fg of t, and you have, this is again so we have again Bernoulli numbers in the game. We have 2g minus 2 factorial, and then we have here the polylogarithm function, e minus t. You haven't never seen this function. This is, xn by k to the n, sorry, xk and k to the n, okay? So this is this famous function, and you see that you can actually expand this, this is going to be, you can expand this naturally as a series in e to the minus t, so you can actually write this as follows, and g e to the minus dt, and actually each of these terms is going to be a Wall-Street instanton. It's a map from a Riemann surface sigma g to the Calabi-Yau M. In this case, the Calabi-Yau M is this. So you are mapping sigma g to P1, and the coefficient that appears when you expand this function is this famous Gromov-Witten invariant. Okay? And actually, this formula was obtained by Faber and Pandaripande, who are algebraic geometers, by doing an actual counting of Wall-Street instantons in the resolved conical. But what we want to understand now is, sometimes you don't want to, you don't have to know all the details of how the formula is derived. What we want to understand is what this formula means in terms of the asymptotic behavior of the genus expansion and in terms of resurgence. So the first thing to look at this is to see if this is going to have the 2g factorial behavior that we have here. Let me just mention that this formula is for g greater or equal than 2. For g equal 1 and g equal 2, sorry, g equal 0 and g equal 1, you have a specific formula, okay? But since we are interested in the large genus behavior, this is what we need. And so you see here, the Bernoulli number grows like 2g factorial, but we are divided by 2g factorial, so this is not the source of factorial behavior. It turns out that the source of factorial behavior is the polylogarithm, and the best way to see it, and this is also going to be very useful, is that there is this formula which tells me that here I have a 2g minus 2, and here I can write this as a sum of k over z, t over 2 pi I, k plus t to the 2g minus 2, okay? So you see that is this part which grows factorially. Okay, here we have the factorial growth. And actually a very interesting consequence of this is that if you put together, if you use this formula here, you see you will partially cancel this factorial behavior, and then I can write this in this form. I can write this as a sum over k in z, and then I have b to g, and just plug this formula in here, so I get 2g minus 2, and then I get it, so I put also the minus 1 to the g minus 1, I insert it inside here, and I get it plus 2 pi k to the 2g minus 2, to the 2 minus 2g. Okay? But we have seen this formula before, because when we were studying the Gaussian matrix model, we actually found the same thing, but just multiplying it to the 2 minus 2g. Okay? So this is actually like a sum of Gaussian matrix models, okay, in which you have an infinite sum of Gaussian matrix models labeled by k. But remember that in the resolved conifold, we found that the location of singularities was actually L times A, where L was a non-zero integer, and A was 2 pi it, right? Now here is just going to be the same thing, just that you have an additional it. So already from the results that we had before, we can see that the Borel singularities for the Borel transform of this quantity are going to be at L times AK, where AK is actually 2 pi t plus 4 pi square ik, where k is an integer. So here we have a more complicated pattern of singularities. If you draw these singularities in the Borel plane, you will see that we have something like this. So here we have 2 pi t, and this choke is not very nice. Let me use this one. So here we have, okay, that's better. So we have a tower here, okay? And then, you know, we will have also multiples of this. So if you take a ray here, and you take a ray there, so this is 2 pi t. This is going to be 4 pi square I, and so on. And here you will have double of this, and you have a pattern like this, okay? So we wanted to give a kind of fancy name to these patterns, because, you know, this you see like you have like towers of singularities, and then, you know, we realized that when a peacock opens its tail, you know, you can see there is a picture in the lecture notes. The tail of a peacock is made of rays with some sort of eyes, right? So these are the Stokes rays are actually like the rays in the peacock tail, and these singularities are like these figures in form of eyes. So we call these peacock patterns. And I remember I was proposing this name to my collaborators, and, you know, one of my collaborators is a mathematician, and he was not very happy. He said, no, this is not serious. And I told him the story of how people came with the name of penguin diagrams in quantum field theory, and then he was convinced, okay? So, you know, so let's have our own penguin diagram here. So this is the peacock pattern. So that's the story for Borel singularities. Now the transeries appearing here. So the series appearing here, the transeries are just the same ones that we found for the. So this was for the Gaussian matrix model, right? Remember that there the singularities were of this Pasquetti-Schiappa form. So here are also the Pasquetti-Schiappa form. Actually, the calculation of this was in the same paper that Pasquetti and Schiappa wrote to do the Gaussian matrix model. So that's it. But now, so this is the kind of formal analysis. But now the question is, how do you interpret these Borel singularities? Okay, and the right interpretation of these Borel singularities is, and, you know, now you can say why you are saying this, is the following. We know, and this is also actually work by Rajesh, that these free energies can be obtained by integrating out D0, D2 branes in the Calabi-Yau, okay? So if you look at this Calabi-Yau, there is the only place, so you think about this Calabi-Yau as a 6-dimensional Calabi-Yau where you do your compactification and you want to see the physics in 4 dimensions. This is actually what Lara has been explaining us how to do. So you look at this 4-dimensional physics, and then if you have, say, a D2 brane wrapping a 2-cycle, this will lead to a BPS particle in 4 dimensions, okay? And then you try to calculate these quantities by looking at the contributions of these BPS particles. This is the famous work of Gopa, Kumar, and Baffa. And the important point of that work is that it taught us that topological strings can be understood in terms of D-branes. So here, for example, you would have a single D2 brane wrapped in P1, and on top of this D2 brane, you can bound as many D0 branes as you want. But this is exactly the pattern of Borel singularities that we see here. You see, this 2PT is the volume of the D2 brane, and this tower, this tower is the new ingredient that we haven't seen before. We haven't seen these towers in the Gaussian matrix model. We haven't seen these towers in 2D gravity. We see them here for the first time. These have to be interpreted as K D0 branes wrapped, attached to the D2, okay? So you can think about these Borel singularities here as coming from a tower of D2, D0 branes, okay? And this is a very beautiful way of understanding the structure of Borel singularities. So the structure of Borel singularities is telling you on the nose the structure of D2, D0 branes that you have. Of course, Gopakumar and Baffa thought that you can also see this looking at here, but here is in a sense less evident. You see, here you have to do a Schwinger calculation, and then and then when you expand in the genera, you get this. But here, it's just the singularities are D branes. You don't have to do anything else. You just see them. Each point is a bound state of D branes, right? So that's a very powerful picture, and it turns out that this picture is quite general, and I will try to justify to you why, okay? Now, before I get into more complicated cases, let me make a comment on mirror symmetry here. So the resolved conifold has a mirror. So mirror of the resolved conifold can be written as a curve. So actually copy it here. So the curve is e to the x plus e to the y plus e to the minus y plus x plus e to the minus t equals 0, okay? So this is, actually this is obtained by the same techniques that one uses in compact mirror symmetry, but then one gets a curve like this, so t is the parameter, and then if you solve for y, you see that this is going to be a log of some algebraic function of x, okay? And actually, you can also see that, if you think about this as a curve, okay, you can actually see that this function will have a branch cut at AB, in an interval AB. So there is something of the structure of one-cut matrix models that survives here, and one can actually see that yx dx between A and B is going to be proportional to t. And then, of course, if you have a log, and the log is multivalued, you will have here a multivaluedness, which actually leads you to the possible D0 branes. So you see here that now the spectral curve, when you solve it, is not going to be purely algebraic. There will be logarithms, but you need these logarithms because it's the multivalues of logarithms that tells you that periods are going to also include these D branes, you see? With the appropriate factor to pi, you will actually reconstruct the possible number of D0 branes as the possible branches of the log, okay? So this picture there is, if you want, a dual picture in which the D0, D2 branes appear as periods of the mirror curve, okay? So that's, so again, we are using this differential yx dx, and the mirror curve is regarded as a spectral curve on which the periods are going to give you the possible locations of Borel singularities, okay? Actually, in this case, actually, you can actually get a density of rho x out of y, which is normalized. And this is a density of eigenvalues in a model, in a matrix model, in an actual matrix model, which is called the Chern-Simons matrix model. And this is also related to this Kopa-Kumar-Baffa duality between the resolved conifold and Chern-Simons theory. I make this comment as an aside. What is important here for the picture is that Borel singularities are telling us about bound states. And in the mirror side, you also see the possible location of singularities as periods of a differential form, okay? Okay, so now how do you generalize this? Well, again, this is relatively easy to generalize, at least in some directions, because we can now, so this is just the resolved conifold. It's a very special Calabi-Yau, but it turns out that there is a piece of the free energy of any Calabi-Yau, including compact ones, which is exactly like the resolved conifold. And let me actually explain you how this goes, because this will give us further insight on this picture, okay? Well, you see there is this very unifying thread in which in string theory, resurgence is always related to the existence of deep brains, and you always have some sort of two pictures. You have the direct picture in which you see the deep brains, you know, and at the same time you have all these mathematical constructions, usually based on a more geometric setting, in which the location of the location of Borel singularities appear as periods of a differential form in the right geometry, okay? In the right geometric context. So this is, I think, a very beautiful unifying picture. So, so let's then consider an arbitrary Calabi-Yau manifold M. And what can you say about Fg? Well, you cannot actually write down Fg in closed form, but Rajesh and Baffa found this famous Kopa-Kumar-Baffa formula, which gives you a formula for, in a sense, it's a resummation of the Gromov-Witten expansion at fixed degree and genus by genus. So they wrote that so they wrote, in a sense, a formula for the full free energy, which is written like this. So it's a relatively complicated formula, but I think it's one of the most important formulas in string theory. It's definitely one of the formula that in string theory which has more impact in mathematics, that's for sure. And then we have something like this. W dt. Now this formula is very interesting from many points of view. So let me tell you what this is. This is G string. So this is the string coupling constant. This is a number which is called the Kopa-Kumar-Baffa invariant. And here you have this d, which is the degree. D is the is a vector of degrees. So you can think about this as giving me the possible topological degrees, or the possible, they are really giving me the homology class of the two cycle where this was instanton n. Okay, so you can think about this as a geometric, the instanton numbers for Worthit instantons. Now, this formula is very interesting. It's not really a series in G string, so this is very different from what we have been doing so far. So far, I have always considered, you know, that actually maybe I should have written a formula here, but you know, the standard picture is that you actually consider an asymptotic series in the genera, in which a fixed genera you have this function, and then you have G string, okay? So the Kopa-Kumar-Baffa formula is not an asymptotic expansion in GS. It's actually a series in e to the minus t, in which each coefficient, it's a non-trivial function of GS, okay? So, so you see, the thing is that each of these quantities is a series in e to the minus t, And then, in a sense, you exchange the order of resummation and you resum partially the series on yes. And then, you could say, okay, then it's done. We were so worried that this is an asymptotic series. So what? Now we have this very nice formula. And then, this is all, right? We don't have to worry anymore. This is a function. Well, this is actually not a function. And the reason is that there are poles in GS here, which are significant. So this essentially means that at every order in this series, the coefficients are all ill-defined. Say if you take GS to be a rational number, there will be an infinitely dense set of poles. So essentially, this is a very strange function, actually, you think about it. And also, if GS is real, if GS is complex, this function, this series actually is worse than factorially divergent. So it's not really the solution of our problems. You can think about it as a way of encoding the information on these FGTs in a very clever way, okay? And of course, they define these Gopakumar-Buffer invariants, which are integer numbers. And these Gopakumar-Buffer invariants count D0, D2 brane bound states in the homology class D and with a spin R. The R here, you have to understand it as a spin of a particle in 4 dimensions. So these count these count D0, D2 branes. Now, in the resolved conifold, you can see that in this case, you can actually interpret this in terms of Gopakumar-Buffer. So this formula actually comes from the Gopakumar-Buffer formula. When you have only one non-zero Gopakumar-Buffer invariant, which has 0 spin and degree 1, and is equal to 1 and 0 otherwise. Okay. So the resolved conifold, in a sense, you can think about it as the simplest geometry, because it has a single D0, D2 brane wrapping a cycle of degree 1 and with spin 0. Okay? Everything else is 0, so that's another way of understanding the simplicity of the resolved conifold. But in general, you have this very complicated formula. Okay? Now, let's try to see what this formula tells us for the problem of resurgence. And the thing is that if you now use this formula, you can actually, it's a very easy exercise that I think I propose it in the notes. You can actually use this formula to find a formula for the FGs of T's for any FG. And what you will find is that this is a sum of D and 0D. So the particles of spin 0 appear first, and then you have this here. And then you have this thing here. And then you have more stuff, okay? So this is a universal formula. This is true for any Calabi-Yau. And you see that the starting point of this formula is exactly like the formula for the resolved conifold, okay? So, of course, there is a lot of stuff here that I'm not writing, okay? But what is interesting is that this part here is a sum of terms, and none of these terms grows factorially by itself. But this term, we know it grows factorially by itself, okay? Because we just saw that this grows factorially. And when you think about this part, which is a universal part of any Calabi-Yau, it's just a sum of resolved conifolds. It's a sum of this type of function, but now you have to sum over all possible degrees and with a weight given by the Gopakumar-Buffer invariant, okay? So now let's go here and let's try to understand. Let's imagine that the FGSTs were given by this formula. What this would imply from the point of view of resurgence? Well, from the point of view of resurgence, we know that this will give you a 2G factorial, so you can try to find what are the singularities. You see now in this formula here, you will have, let me write it like this, you will have an additional sum over D. Then you will have here I dt, right? And then you will have N0D. But this is all the modifications you will get, right? So it's clear what is the modification that you get here. Now you will get a tower of singularities. So you will get a new tower of singularities. So the Borel singularities here are going to be given not by this formula. Now we will have a more general formula but they are going to be given by this, dk, and then L, remember, is a non-zero integer, and then A dk is going to be given by 2 pi d times t plus 4 pi squared ik. So you still have a pattern of singularities like before, but of course now, for all the d's that give me a non-zero Gopa-Kumar-Buffer invariant, you will have a singularity. So here you will have, I don't know, 2 pi t, let's say 2 pi d1t, and 2 pi d2t, all the possible d's that give you a non-zero Gopa-Kumar-Buffer invariant, so for which this quantity is non-zero will give you a singularity, and then on top of each one, you will have a tower, okay? Okay. So you see, these are, actually, this is how, the way that Gopa-Kumar and Buffer found this formula is by saying, let's look at D0, D2 brane states in this Calabi-Yau, and then let's actually count the number of spin R particles that they can lead to, and they got this formula. And again, here, you see, these are actually related to D0, D2 branes. Actually, to be precise, because I have not been precise so far, this is actually the central charge of D0, D2 brane. So the modulus square of this quantity is the mass of the D branes. Okay? So these are the location of Borel singularities are, to be precise, given by D0, D2 branes, related to D0, D2 branes, and they give me the central charge of these two branes. So I have all these towers, and each of them comes, so the trans series, if you want the exponentially small contribution around each of them is going to be given. Remember that there was this sum of, that was found in the Pasquet-Schiappa formula. So we have something like this. And then we have A minus L A d k divided by ds. And what is very important is that now, so we'll have sum over L very equal to 1. And here we have a sum over D, because now we have an over K. These are all the, okay, sorry, let me fix the singularity. So we'll have something like this. But then, very importantly, we have here something like this. Okay? So for a fixed D and K, the exponentially small contribution of each singularity is of this form. Okay? So you see, it's the thing that we had before, but now the Gopa-Kumar invariant appears as an overall factor in this instanton amplitude. So you see, the Gopa-Kumar invariant appear in the perturbative free energies themselves, but they also appear in the instanton corrections to the perturbative free energies. Okay? And actually, the right way to interpret this, remember that in front of all these transities, we always have this Stokes constant. Okay? So actually, this is how you should interpret this Gopa-Kumar invariant as a Stokes constant associated to these singularities. Okay? And so, so the picture that emerges is that, in these Borel singularities are represent D0, D2 branes, but now I have another entry in the dictionary, is that the Stokes constants associated to these the singularities are not going to be trivial, are going to be non-trivial numbers, and these numbers are important numbers counting BPS states in string theory. Okay? So that's the picture that emerges. And let me actually point out something very interesting. When there was a long discussion in algebraic geometry of Calabi-Yau manifolds about the meaning of the invariants. I told you that these invariants count curves, but if you actually look at these Gromov-Witten invariants, they are not integers, they are rational numbers. Okay? And then there was a lot of discussion that, that these rational invariants, they could make into integers, and this was already pointed out for genus 0 by Candelas de la Osa and collaborators in the first paper on mirror symmetry. But then, Gopakura and Baffa said, no, but there are these integer numbers behind the Gromov-Witten invariants, which are very important. Now, it's funny that if one had been able to do a resurgent analysis of the topological strings, one would have found the integer invariance on the nose. These constants are always integers, okay? These numbers are always integers. So of course, historically things happen differently. We had these integer numbers appearing actually when R is equal to 0 for spin 0. This was already originally discovered by Candelas and de la Osa. But it's interesting to know that if one looks at these multi-instanton amplitudes, what appears here is really an integer. Okay, so this is it. Okay, very good. So this already is giving us a kind of even more general picture, and now you can say, well, so okay, see, this is how the ingredients, build up together. But what is the general picture in a Calabi-Yau? So if you give me a generic Calabi-Yau, and I'm going to find, only these singularities, or are there going to be other singularities? And the answer is no, there will be further singularities than these ones. This is not the last words. And one way to see this is actually to look at this conical behavior, okay? Which is another universal aspect of Calabi-Yau manifolds. And you see, if you think about the modular space of a Calabi-Yau manifold, so you think about the values. Let me just take a case of when we have one single Keller parameter. There is this point in which t goes to infinity, and then, the velocity instantons are very large, and this is what is called the large radius point, large radius, and this is the part where alpha prime corrections are suppressed, okay? And now as you move in modular space, you reach, remember, this is very similar to the point where you were doing double scaling. There is a point, t equal to tc, where essentially marks the radius of convergence of these sums, okay? These are sums with a finite radius of convergence, and this marks the nth of the radius of convergence of these sums. So this is very much like the critical value of the top parameter in one-cut matrix models. So this is where the series FGs start diverging, and this, I'm simplifying life a little bit, but this is often called a conical point, okay? This is actually, remember that in the case of the cubic matrix model, there was this point in which, 2 points collided, and, the interval between them became of 0 size. The conical point is typically a point in which, you have an S3, in the B model picture, you have an S3 that becomes of 0 size. And then, you can think what is the behavior. We expect some sort of critical behavior of the theory here, and what is the critical behavior of Fg of t here. And it turns out that there is a universal critical behavior near this point. And this is actually given by, actually, let me write it, this T critical, and let me write it here, maybe tau, okay, 2 minus 2g. So tau is a coordinate, it's a special coordinate such that when t is equal to tc, this is 0. It's a coordinate in modular space which vanishes at this point, and actually tau is the central charge of a D-brane going, it's a D-brane of a state that goes massless here. The fact that here everything is singular is related to the fact that there is a state going massless, and you can think about this D-brane, a D-brane really going massless at this point. And you see, just from looking at this, see, this is the same form that we had in the Gaussian matrix model, right? This is the same coefficient. These coefficients appear all the time, right? This is this coefficient, but now has a different coordinate. It's multiplying a different coordinate, and this different coordinate, this t is not the tau that I'm using here is another parameterization, and this is exactly the central charge of a D brane that becomes massless here. And this D brane, so this means that just by looking at this formula, this means that there must be a Borel singularity at L times 2 pi I tau. So this is another Borel singularity, right? Because tau is not T. Tau is not a D2 brane, generically. Tau is typically a D4 brane, or even in the quintic is a D6 brane, okay? So the picture that emerges is that the location of singularities here is actually quite complicated, because we will have all these D0, D2 branes giving me Borel singularities. Then there will be a massless, we know that near the conifold point there is this massless D brane becoming massless, which is also giving you a Borel singularity, and this is a different one. So the picture is quite complicated, but there is a natural conjecture for kind of putting all this information together. And you see, since this is related to D branes, the way you have to think about this, I have a general Calabi-Yau manifold. How many D branes I can have here, right? I can have in a Calabi-Yau manifold. So you have a Calabi-Yau manifold M. You know, if you want to classify the D branes, the first thing you have to tell me is what are the charges of these D branes, and then we can think about what are the central charges, and then you have to solve the problem of what is the spectrum. Okay. So let's try to explain this. Give a summary of how this goes. Now, the charges of D branes are elements in either the even cohomology of the Calabi-Yau, even integer cohomology. So this is in the type, in the A model. And order can be odd in the B model. Okay? And again, these are exchanged by mirror symmetry. Okay? So we can use the A model and the B model picture. Now, given any, see, this is the charge. If you want, this is the, I call it a charge because, in terms of, when, at the end, these D branes will give me charged particles in 4 dimensions, but geometrically, these are just the cycles that D branes can wrap, okay? So you have a D4, D6, D0, or D2 brane. They can wrap even cycles and give me 1 particle in 4 dimensions, and then you have D3 or D5 or D1 branes, you will have H out. Of course, in the B model, in Calabi-Yaus, we usually have simply connected Calabi-Yaus, so D1 and D3 are not, D1 and D5 do not appear, but D3 appear, okay? Okay, so, so these are the kind of topological numbers of these quantities. And then we have a quantity which is the central charge associated to them. And one, I'm going to simplify a little bit. This is very, very much simplified. Well, let me actually write the actual thing. Because, so in an actual Calabi-Yau, you have this linear combination. So here I wrote so this is slightly more complicated than, okay, I already raised that. Here we have S plus 1 quantities, okay? So it turns out that in a Calabi-Yau, if you want to compute the moduli, you have to compute first what are called the projective coordinates of the Calabi-Yau. So there will be an x0 and then an xi, where I goes from 1 to S, and then the ti's are going to be given by xi divided by x0, okay? And then in the same way, if you want to calculate these charges, these other quantities here, so these fi's, so you have to introduce what is called this projective prepotential. So you have to introduce a quantity I'm going to call f0 of xi, which is essentially x0 squared times f0 of ti. So f0 ti is the thing that we saw before. It's the genus 0 free energy of the topological string. But when you work in Calabi-Yaus, there are 2 ways to parameterize the moduli space. One are you have projective coordinates xi, or you have non-projective coordinates ti, okay? So it's important to have them both because, for example, these zero branes, the ti's give me the areas or give me the Keller, give me the central charge of D2 branes. But if you want to calculate the central charge of D0 brane, you need the coordinate x0. So we need an extra coordinates for D0 branes and for D6 branes. And this is the role of this x0, and also is the role of, actually this is maybe, let me call this f0 here, okay? And now the fi's are just the derivatives of f0 with respect to xi, okay? So these are the quantities that calculate central charge in generic Calabi-Yau's. Now the reason why here we got these simplified formulas is because in toric Calabi-Yau manifolds, so including the resolved conifold, in toric case, you can always put x0 to 1, okay? So when you put x0 to 1, you see that, the only non-trivial variables are these ti's here, okay? But in general, this is a picture that you have in general Calabi-Yau manifolds. And now you can think about Ci and Di are essentially integers, okay? So you can think about the gamma as being a set of, a collection of integers. And this is what appears here, okay? So gamma is the topological characteristic of the D brane, Z gamma is the central charge, and now the question is that these are possible central charge of possible D branes, but the question is what are the actual D branes that you find in a Calabi-Yau? Well, this is actually a highly non-trivial problem, and out of all, remember that you can think about this, gammas as living in a lattice, okay? So giving a Calabi-Yau M and a point, let me write Z as a point in the moduli space of the Calabi-Yau. Then, there will be a subset of gammas which are actually supporting stable BPS states, stable BPS branes, and this it's a subset of the corresponding H of MZ, okay? So, and this is the hard problem in one of the hard problems if you give me a Calabi-Yau, calculating the spectrum of possible branes at a given point in moduli space. This is a very non-trivial problem. And out of this full lattice, not all states are going to be realized, okay? Not all charges will give you stable BPS particles. So maybe some of you are familiar with Seiberg-Witten theory, in which we have a very similar problem. Seiberg-Witten theory, there is a moduli space, which is labeled by the value of the Higgs field in the theory, and depending on the value of this Higgs field, you will have a BPS spectrum. Now, we know that if we're in what is called the strong coupling region, there are only two states in the spectrum, okay? Out of the full set of the two-dimensional lattice of charges in this theory, there are only two states realized in the spectrum, which is a monopole and a dione, okay? So you see that the spectrum can be quite small, okay? But in general, you might have an infinite tower of states in the spectrum. So this is the kind of non-trivial information we have, okay? And now, another important thing is to each point in this spectrum, we can attribute a number which is essentially counting the multiplicity, okay? Counting the states. And this is sometimes called a BPS index, or in math literature is called a Donaldson-Thomas invariant, which is associated to this problem, okay? To this BPS spectrum. Let me make a comment when gamma is you only have Ci different from 0 here, so you have C0 equal to K, and then C1 Ci equal to Di, okay? Then omega gamma is our old friend, the Gopa-Kumar-Baffa invariant D0, 0. Okay? So precisely when the D branes are D0, D2 branes, this BPS index is the zero spin Gopa-Kumar-Baffa invariant. Okay, so now the conjecture is obvious, the conjecture to be made. So what is the conjecture? So if you take the FG of T, or actually in a more general Calabi-Yau, I should use also X0 here. You have this Xi, the resurgent structure is the following, right? So first of all, Borel singularities are located at Z gamma, where gamma is in the spectrum. And this depends on the particular point you are. So you want, this depends on the values of the Xi's or the Ti's. This is just the enlarged version of these Ti's that I did before, okay? So the Borel singularities are located at the brane spectrum, and trans series can be written down explicitly. We know that for this type of charges, these are these Pascuetti-Schiappa sort of multi-instantons, but this is not the most general formula, so it can be written explicitly. And the Stokes constants are the omegas. Okay? Okay. So that's a quite remarkable statement, because it's telling me, you see, these things are in principle computing either Worldsheet instantons, or they are computing, you know, D0, D2 brane states. But what we are saying is that if you know how these FGs behave when the genus is large, or if you want the Resurgent structure, you know the full spectrum of D branes on your manifold, okay? And actually, remember that I told you that in matrix models, what we find is a problem in parametric resurgence. Everything depends on a parameter. Here, also, everything depends on the parameter. Everything depends on at which point in the moduli space I am. And I'm using this notation Z, but you can think about also like Z as parameterized in the Ti's or the Xi's. So as you move in the moduli space of the Calabi-Yau, so as you move in this moduli space, the spectrum of D branes will change. And the Borel singularities will also change, okay? And there are these regions in which you can have this world-crossing behavior, so the number of singularities changes continuously. And this also means that, you know, these omegas turn out to be locally constant functions. They will jump at the world crossings. They are locally constant, but they jump at the world crossings. And this is this famous non-trivial world-crossing behavior of Donaldson-Thomas invariants that mathematicians have studied so much. But the point is that all this, it's contained in the perturbative topological string free energy. All this information is hidden here, okay? And we have seen, you know, partial verifications of this picture by using this Gopa-Kumar-Baffa formula and so on, okay? Now, it's very hard to compute, for example, these omegas from the asymptotic behavior of these FGs, okay? But some calculations have been done, and actually very recently, Simon Duo and Amir Kashanipur and other people have done amazing calculations for local P2, where using I don't know how many terms in the perturbative series, and they have matched very precisely the values of the omegas that are known to appear from other considerations. So this is really this conjecture is very likely to be true. I would bet on it. And it gives, in a sense, it solves the problem of how to understand topological string theory, the resulting structure of topological string theory. Now, let me actually mention that, you know, the typical picture that you would have, for example, here, there is a drawing of the Borel singularities in local P2, right? So for example, this is a drawing that you have in the lecture notes. So here you have the typical picture. Say local P2, you will have a tower of singularities here. And these are D2, D0 branes. So here you have T, or 2 pi T, and here you have the 6 by 4 pi square, and so on. But then you also have, and this is very important, you also have here in the vertical axis, you have a D4 brane, okay, which is the state that becomes massless at the conical. So if you do, for example, a numerical calculation of the location of the singularities, you see these branes. I mean, you see the D0, D2 towers, you see the D4 tower. I mean, there are more singularities which are, hidden here, and, it's a kind of complicated picture. And as you move in moduli space, these singularities move. They can join, they can split. So you have a very kind of complicated set of behaviors that we are still starting to explore, okay? So now a last point that I didn't mention is what happens here. What is the form of the transseries? Because after all, the transseries is what is going to give me the exponentially small correction, right? So let me just write down a final formula for this, because this formula, for example, is useful in other cases. Let me actually mention that, for example, in the case of ABN theory that I was mentioning before, actually in the PhD thesis of Pavel, it was shown that the matrix model of ABN theory can be solved by using topological strings on a Calabi-Yau, and then, then you can use all this information, for example, to understand non-perturbative effects in ABN theory, and you can write down, what are the D-brane corrections in ABN theory, in the ADS dual of ABN theory. So this actually, every time you have a topological string playing a role, you can actually use this information. Let me just finally write down the final formula for this transseries. Of course, when gamma doesn't have, when all these D's are 0, you also only have this Pasquetti-Schiappa type of instantons. But let's consider a toric case. And then, let's consider a singularity which is of the form, let's consider a toric case with one T, with just one modulus. So here, the standard form of the action is something like this, plus C times df0 dft, something like that. And then, well, actually, let me change the notation to be coherent with what I wrote there. This will be the standard, the most general action. So this is the number of D2 branes. This is the number of D0 branes. And this will be the number of D4 branes, okay? Because in the toric Calabi-Yau, the D6 brane wraps the whole space is non-compact, so this brane has infinite volume and doesn't contribute. Okay, so what will be the transseries associated to, this? Well, it turns out that this has a very beautiful formula, so we will have this omega to pi, and then we will have, let me make sure that I don't forget any factor. Yes, we have 1 plus d gs dt f times e to the f t minus dgs minus f t, okay? I mean, there are some corrections that are not, there are some subtleties that I'm writing down, but I want to give you a feeling for this formula. First of all, f here is the full transseries of the theory, so is this function here. And this is a very remarkable result that was obtained, is that the transseries is totally determined by the perturbative part, okay? You don't have to do any new calculation. The transseries is completely determined by the perturbative FGs. And you see this, as you expand here, I mean, I didn't write it very explicitly, but if you expand this, you will get df0 dt divided by 1 over gs times d, which is exactly the action that appears here. So this actually goes like e to the minus a over gs. Okay? So this is exponentially small thanks to this factor, but the formula for the instanton corrections is completely explicit. I mean, you can actually calculate these instanton corrections completely explicitly if you want. Okay? So these are exponentially small contributions of d branes to the total free energy of a topological string. Okay? And you see the Stokes constants are given by discounting of the Donaldson mass invariance. So in principle, the problem is solved. So this solves the problem of finding the resurgent structure. But of course, now the question is, if you want to construct a non-perturbative object, you should do Borel resumations and so on. But at least the possible ingredients that come from the resurgent structure are completely under control. Okay? Okay, I think this gives a kind of complete picture of this. Let me just mention that in the B model, this is a period of the holomorphic free form. So the location of singularities is again a period. So the picture is consistent essentially in all models of string theory that we know how to solve. Okay? So let me finish here.
Okay, before we proceed with the questions, let me remind you that we have a picture taken right after this lecture. Please.
So about this conifold point, I used to think that it's when P1 shrinks to 0.
Sorry?
Like the P1 in the resolved conifold, when you reach the conifold point, yes, the P1 will shrink in size, right? I mean, it will become a point.
Well, the general picture, I think, is that there is always an S3 in the B model that goes to 0 size. In the resolved conifold, yes, you have this that T goes to 0. Yeah, I think the conifold point there is at T equals 0. But this is just a particular case of the resolved conifold. In general, what you have, the universal description is that you have a 3-cycle going to 0 size in the B model picture. Okay?
In the deformed conifold.
In the deformed conifold, yes. But, there are more Calabi-Yaus on the resolved conifold. T equals 0 is the conifold point just for the resolved conifold. In general, it's not, you see.
In general, probably this is the picture.
Yeah, this is a, I mean, this is a, yeah, there is a central charge of a D brane that goes to 0 there. And this, in the B model picture, this is a D3 brane wrapping an S3 or some, I mean, you can have a slightly more general topologies, I think.
Okay. And about this D2, D0 states, I mean, this is in the full string theory, right? I mean, when you want to think of a 10D.
Well, yeah. For example, that would be the spectrum that you would have in type 2A or type 2B, yeah.
Like D2 will be like wrapping a 2-cycle in the Calabi-Yau, but it's like a particle in the 4D. And similarly, D0.
This is the spectrum that you would find for the type 2A superstrings, yes.
Is there an independent way of thinking it just in the topological string?
Well, in the topological string, you can actually, yeah, I mean, you can, for example, study, say, D branes from the point of view of the twisted nonlinear sigma model, which people have done, right? I mean, you can think about also the string field solutions in the string field theory of say, open strings on Calabi-Yaus and so on. Yeah, there are additional pictures like this. Yes.
Okay.
I mean, of course, people have been studying these D branes for a long time. The novel statement here is that this is actually here, containing these FGs, which, this is what's surprising, right? I mean, there were some hints, there were some works where people were saying, well, the topological string free energy should know about D branes. There is this OSV conjecture and so on. But this OSV conjecture, even the statement is not clear. Actually, one problem of the OSV conjecture is that they were trying to use the free energies themselves. And the free energies, for example, you cannot explain the wall crossing behavior of these D branes by using this. The statement here is that the D brane spectrum appears from the resurgent structure of the FGs, not from the FGs themselves. Okay? And that's a very important remark, because the FGs actually do not have wall crossing. The FGs, you can go from here to here, just, I mean, there is a boundary of analytic continuation, but you can go from here to here without noticing anything. The FGs are totally analytic, say, in patches. But the resurgent instructor will change this continuously, even in that region. Okay? And that's what this statement makes clear. Okay?
So maybe I missed something because you were arguing just over there that the Borel plane sort of misses something, singularities associated with the D4 branes. But then
I didn't say that, I guess. I mean, the Borel plane shouldn't miss any singularity, right? What I said is that just from the Gopaku-Marvafa formula, you only get on the nose D0, D2 states. But if you look at other characterization of the free energy, you will find other states already. Just from the fact that there is this conifold point, you already know that there are more singularities in the Borel plane than just these D0, D2s, okay? That's what I said, I think.
Okay, so it is not something analogous to what you were mentioning about the double well in quantum mechanics, where there are some parts missing.
No, I think here the statement is that, well, that's a very conjectural statement. But the statement is that, you know, all the full spectrum of VPS states should be realized as Borel singularities on the Borel plane. But this is a conjecture. This is a conjecture. I mean, this is very hard conjecture, not even to prove, even to check is very hard. Okay? I mean, we have all evidence pointing in this direction. We don't have any counterexample, but this is not, this is a very difficult conjecture to actually to prove and to study. But I would expect that there are no empty slots here. Every stable D brane will appear as a singularity in the Borel plane.
Thanks.
So you mentioned that Borel singularities on the mirror curve, like if you consider a mirror map, they become periods on the mirror curve. Is there any analogous interpretation of the Gopaku-Marvafa invariants if you consider mirror map, if you treat them as Stokes constants, as you wrote down?
Well, in the V model, the picture is the same. I mean, the pictures are completely interexchanged. Now, you could say, how do you compute FGs in the V model if this includes the Gopaku-Marvafa invariance? And this is actually a very non-trivial statement, because the way you compute FGs in the V model is by doing what is called Kodaira-Spencer theory of complex deformation structures, of the deformation of complex structures. So it's really a very I mean, you don't see any integers, you don't see anything. You just see integrals of periods, generalized integrals of periods on the model space of complex structures. So there, in the V model, already the Gopaku-Marvafa invariants, you don't see them, right? So at the level of the FGs, okay? Now,
okay, so I guess there is no simple interpretation of them on
at the level of the FGs. Now, in the V model, you can think about D3 branes, and these D3 branes will come with these Donaldson-Thomas invariants, and there, yes, you should see them. I mean, by mirror symmetry, we know that this counting of D branes and this counting of D0, D2s, for example, should also appear, right? So yeah, in that sense, yes. By mirror symmetry, you know that the spin zero Gopaku-Marvafa invariants are going to be obtained by doing counting of the 3 branes on the mirror. That's true.
This will be the last questions. Other questions you will be able to ask during the
discussion. We have a discussion session in the afternoon, so yeah.
So just a brief one. First, really beautiful overview of this. I was just curious, in the case of compact Calabi-Yau's, the conifold point is like one of 3 degenerate behaviors that can appear on boundaries of calocones.
Yes.
The other 2 being divisors collapsing to points, so complex surfaces that collapse to points, or complex surfaces that collapse to curves, like a curve of AD singularities. I was just wondering, has anybody looked at, this sort of structure in a non-compact setting for those other two cases?
No, that's a very good question. I have to say that the number of, for example, when we studied compact calabiyaos, we focus on one parameter models, right? Where I think this behavior, there is a family of one parameter calabiyaos where you have, standard conifold points. So we didn't see this sort of behavior. So this is still we are still exploring these possibilities because actually the main tool we use is to have as many FGs as possible, and this is very difficult to have them in generic calabiyaos. So we don't. I mean, the answer is we have not studied these more general conifold type of behaviors, but I think it will give probably a new insights on how the D-brains appear in this story. Yeah.
Thank you.
Okay.
Let us thank Marcos for the lecture course.